Welcome. This video is going to continue looking at problems from Section 3 of Chapter 1 in the Brown IB textbook. So question number 40 tells you have methanol that can be made by the following equation. And they've said you have a reaction mixture of 12 grams of hydrogen and 74.5 grams of carbon monoxide. So you want to know your theoretical yield, which would be in grams, of CH3OH. So that's another way of saying what's your limiting reactant. And you may remember that the way I like to do limiting reactant is I would take the 74.45 grams of carbon monoxide. Since it's only one oxygen, this is going to be 28.01 grams per mole. So 74.5 divided by the 28.01 gives me 2.660, we'll go with for sig figs, moles of CO. And since this equation is balanced, I see there's a 1-to-1 ratio of methanol with CO. So this is also the yield I can expect from, this is my CO, will yield 2.66 moles of CH3OH. So then I could go ahead and compare that, oops, I'm not on B yet, I could go ahead and compare that with what the H2 will yield, and 12.0 grams of H2 divided by 2.02 is 5.941 moles of H2, and this is in a 1-to-2 ratio of methanol to hydrogen. So this actually yields 2.970 moles of CH3OH. So my theoretical yield is going to be limited by my carbon monoxide to 2.66 moles. So that means to go ahead and get my yield in grams, I could take my 2.66 moles of CH3OH times the molar mass of CH3OH, and I'm getting a yield of 85.25 grams would be my theoretical yield of methanol. So then part B asks you to find the excess reactant, and this isn't as difficult as it appears to be. The way I like to do it, and there's multiple ways to do it, I notice my yield is staying down there, but what we know is that we had enough hydrogen to make 2.970 moles of CH3OH. And again, there's multiple ways to do this. This is just the easiest way for me to think through it. So if you find a way that makes more sense to you, absolutely do it your way. So what I did actually make was 2.66 moles of CH3OH because I was limited to that by the CO. So if I subtract these two, I'm going to come up with 0.31 moles of CH3OH that I didn't make. I had enough hydrogen to make it, but not enough carbon monoxide. So then that means this 0.31 moles of CH3OH could tell me how many moles of hydrogen I had left unconsumed, because there's 2 moles of hydrogen for every 1 mole of methanol. So then this is really 0.62 moles of hydrogen that didn't get used. And if I multiply that by the 2.02 grams per mole in hydrogen, I come up with roughly 1.3 or 1.25 grams of hydrogen that would be left in excess. Number 41, again, has given us the mass of each reactant and wants to know how much product can be made. This nice reaction because it's all 1-to-1. So I need to take my 15.4 grams of C2H4 and determine how much product that could make. So 1 mole, 12.01 times 2 plus the 4 hydrogen is going to give me 28.06 grams. So then the 15.4 divided by the 28.06 is 0.5488 moles. And again, since this is a 1-to-1 ratio of product to reactant, that's how much product I can expect from the C2H4. So we'll compare that with how much product the Cl2 would yield. 3.74 grams of Cl2 weighs 70.9 grams. So it's going to yield 0.05275 moles. It's also in a 1-to-1 ratio, so this is definitely my limiting reactant here. So if I'm limited to 0.05275 moles of C2H4Cl2, then I need my molar mass to finish the problem. So I have 98.96 for my molar mass times just 0.05275 moles. I could expect a yield of 5.22 grams. Question number 42 gives you some information that calcium carbonate and sulfur dioxide can react to produce calcium sulfite. And what they don't tell you is that CO2 would also be a product, which really doesn't matter because they let you know it's all equal molar, which means 1-to-1-to-1. And then they let you know that you had 255 grams of the calcium carbonate reacting with 135 grams of the SO2, and the actual calcium sulfite recovered was 198 grams, so they want to know what the percent yield is. Well, I'm going to have to find my limiting reactant once again, so the 255 grams of CaCO3 is really, when I divide by the 100.09 grams per mole, I made 2.548 moles, and again, this is the CaCO3 I'm working with, and since it's molar amounts, that's also going to be my yield of CaSO3. And so if I take the SO2, 135 grams of SO2, looking at its molar mass of 64.07 grams per mole. So 135 divided by that molar mass is 2.107. And remember, they said everything was equal molar. So here's my limiting reactant, is the 2.107. So the theoretical yield would be based off the limiting reactant of 2.107 moles of SO2 yielding that many moles of CaSO3. So now I could go ahead and multiply that by the molar mass of CaSO3, which I'm finding to be 120.15 grams, times the 2.107 is giving me 253.2, we'll round to, grams. That's the predicted or the theoretical yield. So my percent yield then is going to be my actual over my theoretical times 100%. So my percent yield, 198 out of 253.2, is a 78.2% yield. In question 43, they describe a reaction called esterification. You make it an ester, and these are really fun to make, and we'll make them later in the year when we get to organic, and these formulas will make more sense. But the bottom line is this is just a limiting reactant problem that you need to calculate your theoretical yield so we can see how much ester we actually made. So I'm going to take my 3.58 grams of CH3COOH and divide by my molar mass of 60.06. So when I go ahead and do the math, I'm coming up with 0.05961 moles of my reactant. That's also going to be the moles of my product, since once again I've got a 1-to-1 ratio here. So if I do the same thing with my other reactant, with my alcohol, 4.75 grams, divide by my molar mass of 88.17 grams, I'm coming up with 0.05387 moles for my other reactant. So this is my limiting reactant. So I could go ahead and find out what the yield should be if I figure out my molar mass for my ester that I've made. So with the molar mass of 130.21, my theoretical yield is 7.014 grams. So if that's my theoretical yield, and I know I'm going to get 45% of that, I can just multiply it by 0.45, and I should expect to have 3.16 grams of my ester. So I'm going to go ahead and do 44 and finish off this section in this video. You're given 100 grams of chlorobenzene as the actual yield you need to come up with. And you're told you have a 65% yield. So what's the minimum amount of benzene you should be using? So first thing I need to know is, what is my theoretical yield? If my actual needs to be 100 grams and I'm only getting a 65% yield, I need to take that 100 and divide by the 65%. Because remember, in math, what we're really thinking is 100 is 65% of what? So when I do that, I come up with 153.8 grams is what we're really looking for here. So that 153.8 is the amount I need to change into a molar amount to determine my benzene. So my molar mass is 112.56. So 153.8 divided by that means I need 1.366 moles of the product, and since it's in a 1-to-1 ratio, that's also how much benzene I need. So if I have 1.36 moles of benzene, and I find benzene's molar mass to be 78.12, and I multiply that by the 1.36, we're looking at 106.2 grams of benzene needed.